Okay, let's look at how we would actually filter out that training data if we had some scores. If we had already built a model to classify the data, and we've already ran that model against all of our training data, and we pretty much have a classification report of all of the audio files in 512 widths, chunks. In terms of the spectrogram, right? So 512 frames of spectrogram every 512. We've already taken that data, ran it through our model, and we have a classification back from it. We'll look at how to actually do that in another video. It's pretty cool. It's like a containerized task that we can put on a Kubernetes cluster and just spin through all of the data. But anyway, for now, let's look at if we had that data, where we would use it to filter out our training data, which is pretty easy. We have the same libraries as we had before here. The only real thing that we're changing is this width. Before we had 512 frame widths, and now we're moving that down to 192, which is about 3 seconds. And then we're skipping it by 128, which is a quarter of the width that we'd used before. It's important information to know later on. But we're shrinking the skip out because we are shrinking the width. And we're doing this because previously we trained a model, and we were not 100% confident on our labels. Essentially, we took all of our audio files into different bins, and we knew that the majority of the audio files in that bin should be accurate, right? The ones in bin 2 should actually be of bird for class 2. But we know that they weren't fully accurate. Also, not all the audio file is actually of that bird. A lot of it's non-bird audio, right? It could be people talking, it could be background noise, it could just be quiet parts. So that's what we're doing here, is we are just whittling down that audio file and trying to find the actual pertinent parts of it, just by using machine learning, right? By first putting them all in the bins that they're supposed to be in, taking big chunks from them, training on those big chunks, using that trained model to filter the audio back down, and then training again with smaller chunks in an effort again to filter it back down. And then maybe train one more time on a very nice model that's efficient in what you want to deploy. So, yeah, that's why the width is smaller here, and the skip is a little bit smaller. But important to know, 1/4 of the width that we had before. Okay, so same thing as before, we're bringing in the Florida Birds JSON file, same exact data, except now we have this scores.json file, which is an object where all of the keys are the asset IDs and all of the values are a CSV list of the scores. So for every 512 chunk, if the model predicted it's a class 2, then class 2 in the list. Right, so we went over every chunk doing that. Download and wave, create spectrogram. These are the exact same as before. Download and wave, we were just downloading our MP3 file, and then we're using FFmpeg to convert it to a mono 16K wave. Create spectrogram, we are taking an audio data, chunking it up into NFFT length units, and calling the fast Fourier transform function on it to convert it. Then we're taking the log of that, make sure all of our numbers are valid, and then taking the mean of it too, so that way it kind of helps normalize all the audio, right? You don't know which one's loud, which one's quiet, what microphone's used. It's just a simple way to normalize it. Okay, then here's where we're actually filtering it. Here's where we're creating the spectrograms, right? We remove our spectrogram folder and we recreate it. And then we have this function getBird, and we are mapping getBird over our list of birds. So we can parallel process all this and make the training data as quick as possible. So our function fires up, it sleeps some random amount of 10 seconds, so that way hopefully they don't all start at the same time. It makes the directory for its spectrograms, grabs some bird info, grabs a list of audio files, and then we enumerate through all these audio files up to some max amount. Because some birds have like 1,000 audio files, and this is not the production level deployment yet. We're just kind of making sure that this process works. Okay, so here we are setting a score index to -1, and then we're trying to get the asset scores for this audio file. If for any reason they don't exist, we're skipping over it and we're going to the next one. And then we're reading those scores in. Like I said, it's a CSV list, so we're reading it as CSV data and splitting it on the comma. Then we're mapping integers over it to get integer values all out. Downloading our WAV file. Again, taking our WAV file, converting it to float32, creating a spectrogram from it, enumerating over that spectrogram into by skip amount widths. And this is where that whole our skip amount is 1/4 the amount of the previous window size is important. And also why we were setting this score index to -1. It's because our current window sizes are 1/4 the size of what they were before. Or it takes us 4 times of getting audio data to go through one window unit from before. Right, one window unit from before was 512 units. So that's what we're having to count up our windows, because it's every 4 amounts of audio that we've slid through, because our skip's 1/4 the window size, that it comes back, and then we actually have to look at the next score index. So that's what we're doing here, is we are increasing it every time that the remainder is 0 after dividing by 4. And then we're grabbing the actual asset scores. We're looking if the asset scores at that index equal our burned index or not. If they don't, we're continuing on to the next. So we're just not making the spectrogram at that point. Yeah, and then if they do work, if they do match, then we're creating the spectrogram, we're saving it to disk, and so that way later on we can read it and create TF records from it. And we do this last part just by mapping a pool of 16 cores over this list of birds that we created from the Florida birds. So parallel process that, run back down here, and now we can create the TF records from it. This is the exact same thing as we did before, no changes at all, because we just don't have the spectrogram files for the parts that don't match. All right, so nice and easy, because we're just taking the glob of those files, we removed them all, and then we only made the ones that matched. So we're again looping over it by 5400, creating our feature dictionary from that spectrogram file, and writing it to the TF record. And again, mapping 16 cores over it, boom, we have TF records to train on. So nice and easy to filter out your audio data. Make sure that you're paying attention to the window size and that skip amount. Actually, I had to go back and change something because I realized in the middle of the video that it was different. I had set the value to 256 instead of 512, so I was actually skipping over half window sizes instead of full window sizes during the classification side of things. So, thanks for watching.